There we go. Hello everyone and welcome to Handmade Hero, the show where we code a complete game live on Twitch. No libraries, no engines, just us, and a good in-depth look at every last little bit of how a game actually operates. If you want to know how that happens, you have come to the right place. Today we are looking at normal mapping, which we set the stage for yesterday by doing the plumbing that's necessary to kind of get it in there. And now today we are kind of going to try... We're going to start the process. Well, I guess what I should say is we're going to implement the basic normal map operations, but they're not going to do anything particularly useful for us because we don't really have much lighting information to work with. So we're going to essentially try to leave it today with the normal maps working so that next week we can kind of go on a little mini adventure to figure out how we're going to produce some kind of a usable light field that we can sample with the normal maps that we're going to be using. All right, so if you want to follow along at home and you've pre-ordered the game on handmadehero.org, go ahead and download the source code and make sure that you unzip the source code to day 97 because we're on day 98 today. And also, I will be cycling the packs at day 100. So like day 99 will be the last one, Monday I guess will be the last one in this pack, and then I make a new pack. So that way, you know, it doesn't become an infinitely huge archive since I include every day's source code in there. So be on the lookout for that. Eventually when you go to your link, you'll see that you've got options to download multiple packs. There'll be like a 0 to 100 pack, and I'm sorry, 0 to 99 pack, and then a 100 to 199 pack, and so on. All right, off we go. Now, I kind of, you know, I'll be honest with you, I was kind of out of it yesterday. It was not a good coding day. Not sure exactly what happened. Some days you're on, some days you're off. Maybe, I don't know, I think I didn't have any coffee yesterday, and you know how it is when you don't have any coffee all day. So it was a bit of scattershot, you know. Sometimes you're done with the stream and you're like, wow, I didn't explain anything very well, and there were a bunch of typos yesterday. It was just kind of a lousy day. So I don't expect that we're going to have a particularly smooth ride today while we try to work with that code I added because it was kind of in a daze. And so we're going to have to pay a little bit of attention here to what's going on just to try and make sure that we don't have any really stupid mistakes in here that are going to cause problems for us. But anyway, what we did yesterday is we added this sort of normal map branch in here that we're doing for every pixel. Again, this is highly unoptimized stuff that we're doing here. We're just trying to get all of the math worked out properly. So we'll be able to see what we want to optimize when we do sort of a more optimal version of it. But basically what we've got here is we've got the normal map version, which is happening per pixel. And we wanted to kind of sample these environment maps that we had, which we're sort of saying are the things that we'll sort of investigate next week to see what we can do to generate interesting light or areas kind of to sample from. So what we want to do is we want to take these normal maps, which we kind of had a little thing in here that would generate a fake spherical normal map for us. We want to take those and we want to do that sampling. Now, we never actually hooked this up, so I think the first thing we want to do is actually hook up the sphere normal map maker, and then we can try passing that sphere normal map in. And we didn't actually do the sampling over here either. We just sort of returned what the color in the normal map was. And so I'm hoping that that will essentially give us a way to just first verify that our normal maps look at all reasonable anyway. All right, so going from there, here's our make sphere normal map. And basically what you do is you hand it a bitmap and you hand it a roughness. And again, that roughness value is just a material parameter that's getting packed into the alpha value. And like I discussed before, we don't necessarily know if we really want to store all three values of the normal map in here because at the end of the day, it's unclear really what we want to do in terms of that. On the GPU, we'd probably only want to store two, so maybe we do that on the CPU side as well because like I said, our goal with the CPU render is not really to make sure that it's performant enough to run the game. It's more just so that we can learn how everything works and show how to optimize it as well. But at the end of the day, CPUs really aren't made for rendering graphics, although they are getting a little bit more with AVX 512 when that comes out at the end of the year. That was designed for graphics, so you never know. But point being, for the most part, CPUs have not been designed for rendering graphics, and so we can't really expect to match what we were going to be able to do on the GPU at any level of fidelity with the CPU anyway. So let's start by saying, all right, we've got our normal map generator here. I'm going to go in, and when we do our load time stuff, I'm going to have it sort of generate one for us that we can use. Just, you know, something that'll kind of be workable. And we were using that tree, I believe, is what we were using as our bitmap to test with. So I'm going to go ahead and you know, say that we had a tree normal map here, even though we don't. And then I'm going to make it so that when we load this tree, I'm basically going to make a bitmap that will be the tree normal map. So I'm going to say that we have that here, and the roughness for this thing is going to be 0 for now. Actually, I guess technically we might as well have the roughness be 1, which is to say that it is perfectly smooth. Do we want to reflective? We'll start with perfectly reflective. That's the easier one to debug. So we'll start with one that's completely reflective. So what we need to do first is we need to allocate space for this. So I'm going to do a make empty bitmap call, since I think we already essentially have that ability here. We needed to pass it an arena. We needed to pass it a width and a height, and the width and the height are going to be off of whatever the tree's width and height were, right? We're just kind of mirroring that. And we don't need it to be cleared to 0 because we're going to write into it directly. Now, I guess when we do that, I believe the way that we said that we were going to do these guys, we stored them in the transient array. And we could keep doing that. Like, that's where the ground buffers are. And I suppose we can do that here as well, right? We can go ahead and say that the tree normal map comes out in here. And that way you can use the same arena that everything's using for transient state. So, and then we'll go ahead and make that sphere normal map in there. Now, I think that's all we really need to do that. Oops, don't really need that arrow operator there. I think that's all that we really need to do. I can't quite remember if there's any other wackinesses. Let's see, and that is also an address of. So it'll make that sphere normal map for us. We can then start passing the sphere normal map along, because we've got this thing here where we're actually you know, about to use it. So we can pass the tree normal map in there, and that should actually allow us to sample from it. Now we have to now bounce back to the other routine there and actually do something reasonable with that. Okay, and I believe we didn't finish doing any scaling on these either, if I remember correctly. So when we sample out of the normal map right here, all we're doing is we're unpacking it. So they're 255. They're like they're 0 to 255 and 0 to 128. And I guess, well, you know what? I'd have to think about this, but I guess we also wanted to to change the way this is packed. This is not really correct, right? This should actually be 128 plus 127 normal z, right? Because it's always a positive value. I mean, technically, we could just do it exactly this way. In fact, I don't know why we don't, for uniformity's sake, right? We should just be packing everything the same way. Take whatever that normal z is, add 1 to it, and divide it by 0.5, multiply it out. So that seems like a smarter way to go. That way everything is in the same coordinate space. So let's pretend that never happened. And we'll just go ahead and get back in here. All right. So now we've got this thing, and like I said, I don't think we're actually doing any real scaling of the values. We just unpacked them, and we linearly interpolated them. But then once we have our normal, we don't really know what any of it means, right? We haven't scaled it down to the proper range. We haven't adjusted for positive, negative, any of that stuff. So we kind of have to figure out what we want to do with that. And what's a little bit confusing here, and I feel like this is one of those things that's again, it's part of the hacky nature of the problem that we're trying to solve, where we're essentially trying to do some 3D things that are inherently 3D. We're trying to do them in a 2D world. You always run in to these kind of problematic barriers, right? But it's just something to be aware of. If you think about what we're drawing, when we draw something and we've got, like we drew that sphere in there, and we've got things that are pointing like directly at us here. We've got things that are pointing up, sideways, this sort of thing, and they get smaller and smaller, right? What's important to note here is there's never anything that's pointing backwards in z, whatever the z coordinate is relative to this, like what we're talking about here. We're never pointing back into the screen. We're only pointing forwards, right? And so the meaning of these things is kind of hard for us to really intuit, but the meaning of our normals, if we imagine this was a tree, really what we're talking about is the x-axis of our normals is the x-axis of our world, right? The y-axis of our normals is really more like the z-axis. It's the thing that would blend between, you know, sky and ground and then that middle thing, right? So the top, middle, bottom. That's really what the y tells us. And then that z, right? The z, which is sort of saying the outwardness of this thing, that's kind of saying, you know, where you are in here, is really more telling us what direction in y on the screen we would actually be going, right? And it makes sense if you think about it, because really, when you have an opaque tree like this that's facing us, there's no way a normal could ever be pointing behind it that we would see. So there's no way it would ever look upwards in y to, like, you know, if there's another tree behind it, we'd never have a normal in this tree pointing at that tree that was actually visible on the front side of the tree. It's not a thing, right? And so it kind of makes sense. But really what it means is that the x, y, z's in terms of this texture map really map into this way, right? They really map into x, y, and z, like so, right? For a tree. Now, we might also have things like the ground, right? And the ground would have normals that would be, you know, pointing in some direction for the ground, right? For ground, it's a little harder to say what actually we would do. I mean, you know, if these are kind of bumpy, they're kind of bumpy in all directions. Like, the ground actually is flat, so it could point in all the directions of the hemisphere. So in some sense, we have like two types of normal map, right? There's a front-facing normal map, and it looks like this. And then there's an up-facing normal map, right? And it actually has a real XYZ that actually means what it actually means. The X's, the Y's, and the Z's are all actually what they really are. And so we probably have to have two different texture sampling paths, one that handles these and one that handles these. And we would switch between them based on whether we were drawing ground-like things or sort of perspective-y sorts of things, right? I know that's a little confusing, but that's kind of how that works. And it's worth noting that that maybe isn't always the case here in terms of not being able to see behind you. You could imagine in the weird case of like the top-down dungeon-y sort of perspective, which I don't know that will necessarily clone, but let's say that we did. So here's like a Zelda-y style room, you know, that you see pretty often in these sorts of games, right? It's got, you know, some brick walls here and you know, that sort of thing, and it's got a slime mold in it that's sliming around or whatever. Okay, anyway, point being, you've got something like this. These walls, right, do have normals that point in that direction. So, you know, it's not like we're throwing away a bunch of information in terms of here. It's just for things like trees, they would never actually have normals pointing in that direction. But it's possible that we could have sprites who do want to have normals pointing in those directions, right? It's plausible, at least. All right. So off we go. In fact, let me just move us back up here. See this? There we go. So for right now, we're only going to handle those front-facing bitmaps for now. We'll deal with the ground a little bit later in having a separate path. So assuming that we've got our sphere packed in here, when we grab this stuff out, what we want to do here is take our normal and we want to produce those scaled values, right? So we want to take our x of our normal, and our x of our normal, I guess we could just sort of say that this is an unpack normal here, right? So we have an unpack, or it's not really unpack, but it's a scale and bias, or unscale and bias normal. Something that will take in our normal for us and it will give us out a reasonable value, right? And that, I guess I could even do that per component. I'm not sure what I want to do there, so we'll just leave it like this. So off we go. That's one of these guys, like so. So this will return that v4. It'll do the unscale and bias normal here, like so. And what we want to do is we want to produce that result, which basically takes the normal x. It's right now packed from 0 to 255. What we want to do is we first want to change that to the range of a 0 to 1, right? So we kind of have, we've got one of these inverters again, right? So we want to do inf 255, and then we want to change that but from 0 to 1 to -1 to 1, right? So what we'd like to do is start at -1, and we'd like to go from there, you know, twice the range of this 0 to 1 value. And that is just going to happen for all of our components since they're all packed uniformly at the moment. The W, which is the roughness value, is literally just a value that goes from 0 to 1, so we don't have to do anything special there. We just convert it like we were converting a color value, an old school color value that wasn't using the linear packing or any of that stuff. I'm sorry, the sRGB packing. So doing that will produce at least properly scaled normals now. Although that doesn't look particularly good. Did I make some kind of mistake there? I believe that's right. You take the normal x, y, and z. We produce a range of 0 to 1 to 1. We then start from -1, and we add twice that range in. No, I think that's right. I would have expected half the tree to look that way, but I wasn't expecting the other half to look that way. That's a little suspicious, to say the least. All right, so coming back down in here, let me just finish up what we were doing. So after we do the lerp of the normal, which I believe is still probably fine, I have to think about whether there's consequences to the fact that we're using 0 to 255 to encode that range, but I think we could probably lerp and then unscale and bias it into real normal range first. But then we have our thing here where we're doing sample environment, which I thought was going to just draw the normal as a color. In fact, what I could do here, just to start with, let me go ahead and draw literally just that normal. So the texel equals the normal, and like so. And we could also force the texel A to be 1.0 so that there's no frisketing. So there we go. So our color is always black. So we've got something nasty going on there. So I'm going to go ahead and, like I said, since it's been a little wishy-washy in here lately, I would like to step in and just verify that all of my stuff is happening the way that I think it's happening, because you know, I don't have 100% confidence in, especially the code that got written yesterday, but we're still coming off of it today, so you know how it is. All right, so I want to step in here and see what sorts of stuff we're actually getting when we sample the normal map, because like I said, we don't really know what we're getting out of that, so I want to see it. So here's our normal A, B, C, and D. Oops, and D. So when we unpack those, I'm just going to take a look at what we've actually got in there. So I don't understand why all of those would be 0. That doesn't seem reasonable to me. So I kind of feel like that is, well, you know, I suppose that could be, no, I don't really know why that could be. I feel like there should be no places in our texture map except, like they should always be normal, right? So I feel like that's just, that suits somewhat implausible to me. So I want to know why that is the case. I'm going to go ahead and look at the normal map directly. I'm just going to take a look at, oh, no, this is exactly what I was afraid of. Look at this, cut and paste yesterday. Did not even change the normal map we were still sampling out of the texture. It's just ridiculous. I mean, how does that help you? Not at all, right? All right, so we found problem 1. Let's go back there now. Okay. So let's take a look at what our normals look like now. Our normal B is 0. Our normal C, our normal D. Our normals B and D, which are the ones that are 1 away, look like they're totally wrong. So that is not reassuring, to say the least. I'm not sure why that is. These guys look not right either, because that's not a normal. 1, 1, 0 is not actually a normal value. So it looks like we're still pretty janky in here. So I'm going to go ahead and take a look at what that normal map actually has in it. What did I just do? All right, bad key combination there. I invoked the will of Visual Studio, which really you just never want to do. Never a good thing if Visual Studio starts doing its thing. Just always bad. All right, so if we take a look at the memory here, I'm going to look at this as an int unsigned, and so I can start to see what's in there. So that actually looks like a fairly reasonable value by comparison to what we were getting. Let's take a look at some set of those values. That does not look useful to me. Yeah, all right. So I'm going to step out a bit here. I'm going to take a look at what happens when we call make, oops, come out here. I'm going to take a look at what happens when we call our sort of sphere bitmap generator, which is in here. I just want to see what that's doing. Oh, awesome. Yeah, I was right to be leery, let's say, of yesterday's code. It was just not good, right? I mean, how many times are we going to write to this pixel? The answer is we're going to write to the same pixel width number of times. Doesn't seem particularly useful. Usually you want to go ahead and move to the next pixel when you write one. Yeah, just a thought. All right, so taking a look at this guy here, let's also just check this math real quickly. If I remember correctly, I was totally out to lunch on the math as well. In fact, I think if pseudonym73 hadn't stepped in, it would have been a complete disaster. Let's go ahead and generate this out properly. So we've got our bitmap UV, which is just where we are in the bitmap, right? That's going to be the x divided by the width, and so that's fine. And we want that to, yeah, to generate a nice value there for our x and our y. So this is going to be our nx and our ny, I guess, right? And so then our nz, as we were saying before, that should actually just be Pythagorean theorem squared, Pythagorean theorem solved, right? So if we just say, you know, this is the sphere situation. If we just say, all right, we've got a sphere, so this is actually, you know, this is actually one of those three-dimensional fancy spheres. If we've got a sphere and we're looking at this sphere from above, so we're looking at it downward, right? And so we just see a circle. Then at any point here, we could figure out, we know that you know, this is an orthographic kind of projection, so we're looking straight down on the sphere. We know what the x and y is because that's just whatever our bitmap, you know, wherever our coordinate in the bitmap is, right? And so if that's the x and y, we know that that represents some point on the sphere, right, where it's taking the x coordinate, right, and the y coordinate of this thing. In order to know what that z coordinate is, we know that the sphere is supposed to be unit length, right? So we know that the radius here, we know that the r is supposed to be 1, right? So we know that x squared plus y squared plus z squared is supposed to equal 1, right? That's what we want to have be true. So what we need to do is solve that equation so that we can figure out what the z is. So squaring both sides, right, we get this. And if we want to know what the z is, we just have to move the x and the y to the other side, right? So it's that equals z squared, right? So then it's just z equals square root of 1 minus x squared minus y squared, right? And yeah, I believe pseudonym probably did that yesterday for us, but since I was out to lunch, it's good to know someone's got your back. But point being, when I'm actually present, I would be able to think of such things. And there you go. So we've got essentially this happening. Minus and minus, right? Just we want to square root 1 minus the square of the x minus the square of the y. That's our nz. So then we've got our normal, and we know that our normal is just nx and y and z. All right. So now those values all range from -1 to 1. Obviously, our nz never points backwards because, like we said, we don't ever really point backwards. So technically, it only ranges from 0 to 1, but we're kind of ignoring that aspect at the moment. So then we got to pack those in here. We pack those in here by first changing them into the range of 0 to 1 and then multiplying by 255, which should do the trick. And then we go ahead and put that roughness value in there at the end. That should just about do it. We do the truncation and the shifting to put the alpha at the top, which is really our roughness. And then we have the RG's and B's value. Now, that packing is not probably what we really want to see, right? You know, if we think about this, when we do our unpack, it's going to unpack. Is that going to unpack into the proper order? Just want to make sure here. Where's our unpack? Unpack. I'm going to put that up at the top. There we go. Oops. That unpack is actually reproducing it properly. So that's okay. So we're good. So that's fine. So let's see if we're getting any closer to having actual normals coming out here that are actually usable. I hope I still have, yeah, let's say I hope I still have my breakpoint set there. So let's see what these normals are. Let's see what these normals are. I still, like 255, 250, why are we having that as our values? That doesn't make a whole lot of sense to me. Oh, right. That is one of the things that's the other problem that we had before, which is that we have to sort of take into account the fact that we're sometimes off the sphere. So, you know, when we're drawing this guy, since we're filling the whole bitmap, we're going to be filling values in that are actually over here. So we're probably going to want to make up something reasonable for these guys. What we could do is say anything in here just points like straight up or something, right? So it's 0, 0, 1, let's say. Again, there's really not, I mean, I guess, you know what, the other thing we could do is just say it's just whatever the closest value was on the sphere, right? That's the other thing we could do. That seems somewhat reasonable. So what we can do is say, oh, you know what, let's take this and we'll say this is our root term, right? And so there's our root term. And so, you know, once this gets up to the point where it's going to be greater than 1, so the root term goes negative, right? So, you know, the case where, oops, nz, we'll say if root term is greater than or equal to 0, then we can actually do this properly, right? Excuse me. Because the square root will actually be somewhat defined. But once we get to the place where it would go negative, we would be in imaginary numbers, which would not be good. So what we want to do is replace it with something more useful. And in fact, I might actually argue that what I should do, I guess we'll do it like this first. But we might do something a little bit fancier later. So there. So basically what we do is we say, all right, we'll compute this using the square root method, assuming that we're on the sphere. If we're not on the sphere, we'll just assume that it just points up for now. But we probably want to do a little something different later if we ever wanted to use these for things. So let's go ahead and see if that helped at all in terms of dealing with our out of bounds. And there we go. Those are much more reasonable. So those are 0, 0, 1, which is exactly what I would have expected them to be at that point. When we do the lerp, we should get a reasonable result back. Of course, these are all the same, so we should have done the same thing back. And then when we take our normal and we unbias and scale it, hopefully it will produce what we think it should produce, which is 0, 0, 1, which is roughly what it did. So that's good. Although I wonder why we kind of want 128 to map exactly to that So we should probably take a look at that, I think. Anyway, let's take a look at what that looks like first, just for starters here. Oops. There we go. So that's not those. So now we're getting basically nothing is ever inside for some reason, which is a little bit odd. Like, why are we're never getting any reasonable values in there? We're just getting pointing straight up, right? That's all we're ever seeing, which seems odd to me. I'm not sure why we're always filling in that same value. We do the root term here, where we're saying 1.0 minus nx and y. That should be, that should be computing that at least sometimes. Let's take a look at why that is. There we go. So we're never actually getting that value. Okay, let's switch back in there. All right. Could we run, please? Thank you. So taking a look at these values, nx and y, both -1. That's what I would expect, totally reasonable. What's bitmap UV? Should be 0, 0, right? And it is. So as we walk through here, what? That doesn't make any sense to me. Why is that negative? Man, yesterday's code was awful. I feel like this should have been shown, this should have been like on the stream the entire time yesterday. Just like, it should have been the owl sitting there the entire time. This is just ridiculous. That's not okay. Like, how did that get there? This should be that, right? I mean, that doesn't make any sense. Man, when you're not with it, you're not with it. That's just absurd. All right, let's try that one more time. Okay, that looks a lot more like a normal map. So I think we're getting back into a more reasonable space here, if you will. It looks a little janky, so I think we've probably got some stuff we still need to work out. But point being, we're at least in territory that's not totally absurd. So that's good. So, baby steps. Anyway, so there's sort of our normal map, and this is what we would expect to see, right? In fact, we could, just for the sake of drawing it, we could actually rebias and scale it, if you will, inside the render group where we're outputting it as the color. We could actually do something where we say, all right, don't actually draw it in the -1 to 1 range. Boost it up a bit. So multiply this by 2.0 and add 1 to it. I'm sorry, by 0.5 and add 0.5 to it, just to get it back into the valid range of colors. So basically we can see that, in and out we're actually getting the proper stuff, right? And that looks about right. So you can kind of see how you get like the amount of red increases as you come over this way. The amount of green increases as you come down, and so on. And that's just more of a sensical that's more of a sensical thing. You can kind of see how it looks like either our lerp is not quite right or something. We're getting some weird, it feels like we've done something slightly incorrect somewhere in here, and I'm not exactly sure where. So I feel like we kind of want to take a look at what's going on in there a little bit more carefully. Like we shouldn't be having so much jankiness there. Now, if I turn off the normal mapping, if I just get rid of this entirely, my tree, I guess it might be hard to see if the tree was janky, right? Because, I mean, it's not as clean as this is, so maybe wouldn't necessarily show. Maybe what we should do is, instead of using that tree, maybe we should use something that's a very well-defined shape. For testing purposes, that seems like a very plausible thing to do. Just something to think about. But I'm kind of interested to know, like, is it... well, you know what? One thing I could do pretty trivially here, right, is if I go back in here and I say, all right, we've got the tree. If I was to just say draw the tree normal without, you know, just pretend it's a texture map, what does that look like, right? And so here's what that looks like. And yeah, I mean, even looking at, obviously it's doing sRGB weirdness stuff. I'm not sure why this would be yellow exactly. I'd have to think about that. Oh, because it's 128 is the zero value. But you can see that the edges are not all janky as well. So I'm curious as to why our sampling was so weird on the normal map. I feel like it should have not been so odd, right? So I feel like we've got to maybe do a little looking at that code just to make sure there isn't something really strange happening as to why it looks so weirdly banded like that, basically. So when we do our lookups here, we're doing the lookups in the normal map the exact same way that we're doing them in sort of the for the regular texels, right? I mean, there's really nothing. This is the exact same code, right? Ah, there we go. Again, basically today is just fixing all of the bugs that were in yesterday's code. So hey, big surprise, you get the pitch wrong, you sample out of the wrong place in the texture. So there we go, there's our normal map, and that's better. And we could probably turn this into a function too, just to make it a little less error prone, right? We could say, okay, we've got an inline here, which is, you know, something that takes a bilinear sample. So it's like, you know, bilinear sample from one of these loaded bitmaps, right? So we have a loaded bitmap that you pass in, and that's the texture. And then we have, you know, an X and a Y, right? An X and a Y that you wanted to sample at. We can then do all of these samples together, and we could just return those, you know, in a little struct that was like a bilinear sample, right? Like so. And so we could just say A, B, C, D, like we did before, and we'll just do this. Result.A, result.B, result.C, like so, and we return result. So that is that. So let's take a look there. There we go. I'm going to go ahead and change these guys over to that. So I'll do bilinear sample texel sample, something like that. I don't know. Yeah. Call it bitexel. Or, texel sample's good. All right, so we'll do texel sample. We want to do that bilinear sample of the texture, the X and the Y, like so. And then in theory, we should just now be able to do texel sample A, texel sample B, texel sample C, texel sample D, right? Everything's good. And then we can do that here as well. So we got bilinear sample, normal sample, bilinear sample, grab that normal map out, go ahead and get the X and the Y, same thing, and that should be it, right? Just do normal sample A, normal sample B, normal sample C, and normal sample D. Okay. So now we are back to reasonable here, I think, or at least somewhat reasonable. It does kind of look a little odd, like it feels like it's a little clipped potentially. So something else, I don't know if we want to look at a little more carefully, but point being. So if we now go ahead and switch back to this path, we would see our sort of normal map kind of color stuff modulating against the tree. So we know that both of them are getting sampled relatively correctly, so that's good. All right, so I think we're in better shape now. We can actually start to do something here. So the next thing that we kind of need to figure out is what we're going to do with these environment maps, right? Because we need to pass something in there so that we could sample them, right? And we also have to kind of figure out how we want to modulate them in, right? We have to decide what we want to do in terms of actually producing the colors here. Now, what we could do is just say that we add them together, and that might be reasonable. I don't know. I mean, we could say this sort of thing. We just add however much light there is to whatever's there, at the moment. And obviously, we would want to make it so it would not overflow. So for a lot of these, we'd have to actually clamp them, right? We'd have to go ahead and take, after we were done, we'd have to clamp all of the values, right? So our R would have to be clamped from 0 to 1, like so. There we go. So if we add the light in, that's what we're looking at. Also, obviously, well, actually, I guess so. We have another problem here, which is that the light color, this is all pre-multiplied alpha. So our light color, whatever we grab out of the light color, is going to have to be multiplied by the Texel's A value, right? Because the Texel's A value is what actually we're expecting everything to be pre-multiplied by. So that's one more thing that we have to do, right? So now we have our thing, which is lit by our normal map, but our normal map's not actually gathering any light values. So we're literally just using the values that are in that normal map itself to do the lighting, which is pretty useless, right? To say the very least. So what we want to do now is we want to go ahead and actually try to grab that lighting out of something, right? So we got to start tackling our map stuff. Let's take a look at here at sort of what we had yesterday. We did the unscale and bias the normal, so that's all good. Excuse me. Yeah. We're saying we're going to see which NVAP we were using by grabbing the normal Z, but like I was saying, it's really the normal Y that we want to use for that, not the normal Z. The normal Y is what tells us where we are. Now, of course, the normal Y actually goes between -1 and 1, and so this testing is not actually at all what we would want it to be, I think. Right? We probably want something more like this. Again, this is yesterday's code, which is all awful. That's what we've pretty much learned. So what we want to do is say, whatever the actual pointing value is that we choose to use, and like I said, we'll probably have multiple modes that pick different values here, but whatever we choose to use, we say, okay, we've got the env map. If that's less than the -0.5, then we're going to sample from that bottom map. If it's greater than 0.5, then we're going to sample from that top map. We then need to produce how much we want to blend in that top map and bottom map. So for the bottom map, if it's less than -0.5, that means it's ranging from 1.0 to 0.5, right? So in order to figure out what we actually want to do, we need to take the env map and we need to base it off of that bottom value, that -1.0 value, right? So it's subtracting -0.1 or adding 1.0. And then we need to divide it by its total range, which is just the 0.5, right? So that way, like I said, if it's -1, we just end up with 0. If it's -0.5, which is the maximum it could be, then it'll just be 1. The tfar map will be. So similarly, coming here to tenv map, greater than 0.5. So again, same exact math, right? We want to subtract where it starts from, essentially, from it. So now it's ranging from 0 to 0.5, and then we just, again, divide by that 0.5, right? So that should be it, I would think. Of course, dividing by 0.5 is the same as multiplying by 2, so we could just save ourselves the trouble, right? And do it this way. that should give us what we want, right? That should give us what we're looking for. We then go ahead and do our sampling, and we sample at least one of these guys. If we ended up picking one of these far maps, the top or the bottom, that we want to contribute in there, then we go ahead and do our sampling for that as well, right? So to do that sampling, we were passing the normal XYZ. It's a little unclear if that's really what we want. We kind of have to think about this a little bit because, again, like the X, the Y, and the Z, what do they really mean? I guess we can pass them to the sample environment map this way and have sample environment map kind of know what they mean, but it's just one of those things where it's a little confusing, right? So let's think about this for a second, because now we actually have to do this math here. What we essentially have is we have a circumstance where we're looking at a point in the world, and we've essentially turned these into barycentric coordinates, right? We're essentially looking at something, because, oops, that's not what I wanted. We've got our screen space UV, which is sort of telling, you know, it's telling us where we are versus our environment maps, right? So it's kind of telling us like, okay, you know, if it was here, then maybe that's 0.2, right? Maybe this is 0.2 and that's like 0.8 or something, right? That's the screen space U, screen space V. So we know we're like here, and then we have some normal, which is telling us, you know, in this sandwich, you know, this is like the lowest layer of our sandwich, right? Let's say. Well, I guess it's really not. It's the middle layer, right? And then we've got here, here. So from this point, we then have a normal, and that normal is, you know, pointing in some direction. And so now what we need to do is say, okay, for the normal pointing in that direction, we need to figure out how we want to do the intersection. Like we need to figure out how to pick the point where we are looking at, you know, in our environment map, right? And essentially what I said before is that maybe 0.5, we're basically using a 45 degree, I think. Well, I guess that's not entirely true. If it's 0.5, then yeah, I mean, basically what we're saying is the deflection off of the Z is not going to be more than 0.5. We'll have to think about what that actually is cone-wise. But point being, we've sort of got a cone that we're looking up in and a cone that we're looking down in, and we want to produce like which pixel on the map we would hit for each of the normal values inside there. And then when it comes out and it's more lateral, we then are no longer looking in that. We are looking strictly in this sort of middle plane, which is kind of the problematic plane, the one where we don't really know what we're going to do about it. So we've got two environment types. We've got the environment type up here. We've got the environment type down here. We've got two of those that are probably more straightforward to answer, and then the one that's we don't really know what we're going to do with, right? So I think, if I'm not mistaken, this middle sample here, we could just say, for now, that middle sample we know is not happening, right? We know that's not happening. So assuming that we actually have one of these far maps, then we'll sample the far map with that. And of course, again, since it's yesterday's code, it was garbage, and it wasn't even passing the actual map that we picked, but now it is. And so we grab that far map out, and then we actually lerp between the colors based on that. So what we need to do is make sample environment map actually produce some kind of value that we can use here, right? So put this up here. So sample environment map is going to give us hopefully what we want. Given some map that we have, the first thing I think we're going to do is take the roughness out of the equation. So we'll say that we have LODs here. I'm going to get rid of this width, height, power of 2 stuff for now, because we don't actually care about it at the moment. And we'll just say that we have some number of level of details here. What I'm going to do is say, okay, whatever the roughness level is, that's what picks into our LOD levels. And what we'll do is we'll just set all the LOD levels to point to the same bitmap at first. So we kind of take roughness out of the equation, right? But it's pretty straightforward. We just say, okay, however many of those we have, right? Whatever this value is here. So the map LOD, however many of those we have, we just want to essentially quantize this roughness value to fall into one of those buckets, right? And so what we're going to do is say, and later we could, we could actually try to blend between them if we really wanted to as well. But anyway, so what we want to do here is say, all right, we take that roughness, we multiply it by the array count, which will give us back a number between 0 and whatever that level is. We'll do the rounding on it like before, right? And we'll come up with an integer roughness level here, right? So this is our roughness integer, right? And or I guess we could say our roughness index. Maybe our LOD. We'll just call it our LOD index, right? So we do this, and then we want to cast this guy down, right? So we want to say whatever this guy was, we are now going to cast him down into the LOD index, and then we can assert in here as well that the LOD index is always less than whatever that array count was, right? So we shouldn't ever be able to fetch outside the array. Actually, now that I think about it, this is actually supposed to be array count -1, right? Because we want to produce 0, 1, 2, 3. So yeah, I think we actually want to say that, right? Makes sense. So that gives us our LOD index back, and then from there we can go ahead and grab the LOD that we actually want. So now we've got a loaded bitmap, and this is our LOD. So that's our map LOD index. Oops. So once we have that out, we can go ahead and take a bilinear sample of that value, right? And then actually compute whatever that should be, right? So we can go ahead and say, we've got our LOD, and so now we just need to figure out what our x and y coordinates will be in the map. We can take that bilinear sample, and once we have the sample, then we can actually do the lerp on it, right? And what we could do too here is say that, since we already know how all this stuff works, we could also smack this down into a thing, which is that bilinear sample could then have a function that was like bilinear blend. So we could just say as well bilinear blend here. And then we just kind of grab all this stuff up and say that our texel sample can do that sRGB bilinear blend, let's say, right? Like that. And this will basically do sRGB bilinear blend. That'll take a texel sample and basically do all of the stuff it needs to do the lerp, right? So that's kind of cool, because then we can just say bilinear sample, like so. There we go. Although, I need to rename that. And right, we need the FX, FY values. So those are the percentage off that you are. So we need the FX and FY. And now we're back to this. So when we do this, again, we would have to produce the actual color. In fact, I guess I get rid of that and say that the result is going to be equal to that sRGB bilinear blend. Of course, it's only part of it. We don't actually use the alpha component, right? So it's really just that much of it. But there's our sample. And so really all we need to do is actually do that intersection math now, right? We actually need to figure out how we're going to intersect it. Once we do that, we should be just about done. This guy has to actually take the FX, FY as well, right? And let's see, this stuff can all be probably collapsed down into functions as well here. Yeah, because this is all the same as what we would use to sample that bitmap as well, right? We take the U and the V and we expand them out. I'll have to think about this a little bit more. This stuff is all the same as well. I'll copy it for now, but I think maybe we probably just want to condense that down. All right, so we're in here. I'll rename these to the sort of the stuff that we were using before. We'll call this XY, like so. And so now we really just need to know what those values actually are. And I think we're basically out of time. We only have about 2 minutes left. So I don't think we'll have time to cover the intersection math today. I guess we'll have to push it till Monday, which I suppose is fine because that will put us into when we're supposed to actually working on the light stuff that we'd be sampling anyway. Let me double check that we've got everything here. So here is our map, right? Width and height. Our LOD, like so. And I think all this stuff is fine. So we'll just say for now, TX and TY are nothing, like so. Return result. There we go. And this should crash us, I would think. To be honest with you, I do not know why it did not, because we aren't passing valid environment maps. Oh, I guess because we do test it here. So we do test to see if our map actually is valid. So I guess it won't crash us. All right, so we're all good. We just need to actually generate those maps now, which is what we'll do next week, and do a little bit of intersection math right here. Do intersection math to determine where we should be, right? So that's all good. So I think we're getting closer. It's just a lot of work to do here to get all this stuff working, but yeah, I think we're getting closer. Really, we've got everything that we need in place, but we need to do the intersection math to figure out where those things should hit, and then we also need to go ahead and do the production of basically getting the ground and the sky into things that we sample from, if that makes sense. So we still got a ways to go, it's true. But next week should be pretty interesting. We should be able to get a fair bit of stuff there. So let's go ahead and go to the Q&A. Right? I really like whoever said this should crash us, never crashes, and this should work, always crashes. It's true, right? It's like the computer doesn't want to agree with you. It's like if you say that something's going to be okay, then it wants to make sure that you know that that's not true. And if you say that, well, it won't be able to handle this, then it wants to prove you wrong and be like, oh no, it does. It totally works. But yeah, I forgot that we were already checking for that. Normally, when we actually go to optimize this stuff out, there won't be lots of ifs in here. So like normally it would crash us, right? But do we have any questions? Again, most of today was, I guess, just kind of cleaning up everything and fixing what we typed in wrong yesterday. And we, again, did some nice collapsing here just to get this stuff out. And, we'll probably actually honestly have to uncollapse a lot of this stuff in macro style or whatever when we do the optimization. But while we're getting stuff working, it's usually nice to be able to pull stuff out into functions that work, because that way you don't make typos that cause you lots of pain, That makes sense? Let's see. When you lerp two normals, you probably won't get a normalized vector. There are a few things you can do about that. Would you briefly comment on your thoughts about this? Yeah, sure. So I talked about this a little bit. I don't know if it was yesterday. I think it was yesterday. If you remember on the Blackboard, actually, it's up here somewhere. Let's see. Where did it go? Where did it go? This is lighting. Normal maps. Normal maps. Normal maps. There it is. This was the diagram where I was talking about it, right? I was like, when you lerp between them, you get like a stumpy one, which is not really normal. And if you remember what I said back when I was doing that, I was like, well, we don't really need to think about that right now because we don't know what we're actually going to do sampling-wise. And that is true. So if you take a look at what happens here, this lerp is the thing that might produce the incorrect normal. We unscale and bias it, and then we start using it, right? And the question is, well, do we have to correct for that? And so what I'm guessing, and I could be wrong about this, but what I'm guessing is that when we do the math here, because we're actually doing an intersection, we will be able to do it with a non-normalized normal and just bake that normalization into the divide. I think. Don't quote me on that, but I suspect we'll be able to do that. So we'll see. If you can't do that and you actually need an actual normal, then you've got problems. Now, one thing that we aren't doing properly here is we're not doing this selection correctly, right? This is the blend. And so the lerp normal will get the wrong blend amount there because we're just using the normal y directly. And so, I could put a to-do here, and we could also just say, we want to be totally correct for now. And so, do we really need to do this? But we could do, okay, just always normalize, the normal that comes in, right? And that's totally fine, right? Because like I said, this is the slow path right now. We're just doing it for correctness. So we could just always normalize right after you come out. In hardware nowadays, especially if you're on a PC, like on a desktop part, usually they've got fast inverse square root. And so you almost always don't even store both coordinates. You store just the x and the y, and you normalize out to get the z. So like this thing that we did that you in fact recommended yesterday is actually you just do it in the shader, right? So you never actually do this z computation. You just compute it in here, right? Chronal Dragon, how are we going to sample lights when calculating the pixel values for each sprite? Will there be a list of all the lights, or will that be a parameter of some sort? No, it's in a texture. That's what I was saying. That's what the environment maps are. The environment maps, we're going to write all our lights into environment maps and then pull them out that way. So we don't have a list of lights, we just have a texture. That way, it doesn't matter how many lights we have. We could have like 1,000 lights and it doesn't cost any more, right? It's just one way of sort of simplifying things. Ingenero, whatever happened to your almond milk? I was drinking it today. I just didn't put it in one of those bottles. I need a bottle brush. Those bottles are getting kind of nasty and I don't like drinking out of them anymore. So I need a way to like scrub them. Insofar as, well, Yang should be making normal maps for the art now too. I may generate the normal maps as using some kind of offline processing. So I don't know that she'll actually make them. But yeah, we're going to basically try to have normal maps included with the art set. But how they get created, I'm not sure yet. Will you cover more advanced BRDFs or just simple Phong-like lighting equations? I don't know that there's... So like, BRDFs are not really all that useful if we're already totally hacked lighting. Like, BRDFs... you don't really see much. You don't see much of that until you have really obvious stuff happening, right? You got to have like real lighting, a really much more complex lighting environment to really start to see the results of those. So having a BRDF inside a completely hacked lighting model doesn't seem like a particularly productive thing to do, right? It seems like you're just totally throwing cycles away at that point. But I mean, again, it's really pretty simple. If you have a notion of what the incoming light is, you certainly could go ahead and do some light computation. We're not doing even Phong here, right, yet. All we're doing, we're not even accounting for the viewing angle yet. So, if it's something that people want to see, we could do something here where we're like, okay, actually do a lighting model computation here. To basically attenuate that light based on the viewing angle. And so yeah, we could totally do something like that. Because right now, and we also here actually compute a bounce based on the viewer direction, right? So there's a bunch of stuff that we're just not doing. I don't really know if you want to actually do those things. I'll put to-dos there in case we want to talk about them. But again, I'm not sure how useful that is when everything is totally hacked to try and like fit it into the 2D scheme. What if I don't want my game to be just normal? Are there other kinds of maps I can use to make my game more unique? So yes, you can use abnormal maps. And abnormal maps, so basically like where that term comes from is essentially there's a so there's a thing called an A-B normal map, right? Short for, and they're shortened to abnormal maps, right? And basically what an A-B normal map is it's essentially like you take whatever, you know, mapping that you wanted to do, right? So you maybe take a normal mapping, right? And what you do is you make up two other textures, an A and a B. Well, actually, to draw them properly, you'd put them on this side, right? An A and a B. And you introduce operators between the maps, which basically totally ruin the good calculations that you were doing over here, but get you a completely unique result out this side, right? So one thing, for example, you might do here, these could be convolutions, for example. They could also just be straight ahead, like adds or multiplies. So like oftentimes one thing that you might do is like an A times a B times the normal map would be another one that you could do. And that's how you can produce one of these abnormal maps, and then your game looks very unique and awful. Chrono Dragon, some games use a bump map in addition or instead of a normal map. What is the difference between these, and what are the advantages or disadvantages? Well, probably no one's using a bump map for lighting instead of a normal map these days, I would think. If you're using a bump map nowadays, like actually using a bump map, then either you're just trying to compress your normal map more than you could otherwise, and so you're trying to reproduce normals from the bump values, you know what I mean? Or you're trying to use actual displacements or other kinds of like occlusion in the map, so like other effects besides lighting, you know what I'm saying? But the relationship between these is pretty straightforward, right? So a bump map, and this is not a joke like this was, this is actually serious. So a bump map and a normal map, right? What happens is the bump map basically says height, and this says surface direction, right? So if you look at what these actually represent, you know, if I take a 1D cross-section of it, like a height map, let's say the surface goes like this. A height map is just at every texel you just store how high it was, right? So that's a bump map. A normal map, on the other hand, for the exact same surface, right? So these heights actually, you know, just to make it totally concrete, it's this distance, right? That's what gets stored into this map. The actual normal to the surface at that point, right, is what gets stored into this map. So that is what gets stored in here. Now, pretty much you never really want one of these unless you're trying to do something else with it, like I said, unless you're trying to go for better compression because, hey, this only has to store one value, which is that height. Or you're trying to do occlusion, so you need to know what the height was because you're trying to do stuff like if you view it from this angle, you can't see this pixel because this pixel occluded it, stuff like that. There are schemes that do stuff like this. That's for 3D. It wouldn't help you in 2D, but in a 3D game, like a texture, like a brick wall that had like little mortar, you know, in-skews mortar things, that kind of stuff. So what's going on there is basically the surface direction is always a much higher quality way to store this information than the bump. And the reason for that is a surface direction can store anything, including a perfectly, a full-on hard edge here. It can store like things that point directly that way or anything else. Whereas the bump map can never really capture that information because the bump map is not storing an orientation. It's storing like a delta. It's storing like a height that you then have to look at the difference between to compute the lighting, right? Because height doesn't tell me anything that I need to. Height doesn't tell me what the lighting calculation should be. Because remember, I need the tangent plane to do the lighting calculation. So what I have to do for a bump map is I have to look at what the surrounding values are and try to decide based on those roughly what the normal would have been, whereas the normal map just gives me exactly that. So the normal map's always superior if you can swing it. A bump map's usually if either you need to save space, so you don't want to take up as much space as the normal map might take up, or you're trying to get more bang for the buck by getting other schemes out of it. So typically what you might think of is the normal map is sort of like storing the derivative of the bump map. Like if the bump map is this, then this is like, you know, that. And more technically, at the risk of getting ridiculous at this point, it's really this. It's really the gradient of the bump map, right? Which is to say that it's creating a vector that says what direction the bump map was changing in. If that makes sense. And it's even a little, it's even not quite that, because that actually would point, that would give you, if I'm not mistaken, because this is explicit function, and pseudonym 73 can either corroborate or deny this. Basically, you've got a function that's the height, right? And technically, I believe since it's an explicit function, like you've got f of uv and it's outputting this function, I believe technically you take the gradient and you'll actually get this tangent, right? And you want the perpendicular one of that. So I think actually, technically, it's not even really the gradient. What it is it's the cross product, right, of the gradient versus the function, right? So it's that weird. It's like I don't even know what that's called. The curl. I don't even know. But it's like the cross product of that original gradient that you'd get. But that's what you actually want in terms of, you know, taking the bump map and turning it into one of these. So they are related. It's just that this is a much more expressive version, because you'd have to, in order to express all the things you could express with this, you'd have to be able to have like essentially infinite changes in height to sort of say what the normal should end up being at that point. Because you can't really, you know, since these are fixed, you can't ever represent the fact that the surface did things like this, right? Because you can't put two sample points at the same area, right? So it will always think that if you showed it that, it would always think it was this, but really maybe it was more like this, right? I don't know if that makes any sense. Hopefully it does. Will the effect end up like a bump map effect? Yeah, so it's basically, normal maps are basically the more powerful version of a bump map, right? A bump map is like a worse version of a normal map, if that makes sense. Could we do reflections by using our frame buffer as an environment map when drawing the bitmap? Yes, that actually is what we'll be doing. So that's basically how we'll have things sort of reflect the ground and that sort of thing. Again, I'm not sure how it'll work out, but that's just what we're going for. That's like what we're trying, right? If you imagine the surface as an implicit function, it's the gradient of that function. Yes, exactly. Like if we actually had a function that instead of being explicit, so it's not this, but it's like an explicit function, which, I'm sorry, if it's an implicit function, so you actually have a value for it everywhere and you're looking for the iso contour, then it's the gradient, yes. But we don't, a bump map isn't that. A bump map is explicit, so yeah, you kind of have to do the, you kind of have to take this guy, you have to take the tangents, the actual tangents of these guys, and you have to take their cross product, right? So, you know, if you looked at it this way, it's like, okay, so we have, for any point, we have a tangent for the u direction and a tangent for the v direction, right? So we've got these, and we have to cross them to get that normal, right? We haven't covered cross products, and we won't because it's a 3D thing, really, that we probably won't ever need to cover. Maybe we would eventually, but you know, a cross product, yeah. So it would be a gradient, or it's sort of like a gradient, but unfortunately we can't actually do it that way because a bump map is again, it's explicit, not implicit, unfortunately. So, all right. Looks like we have come to the end of the questions. All right, yeah, looks like we're done. Lovely. Lovely. Okay. So let me go ahead and close everything down here. And I saved this, right? Double check. Okay. All right, thank you everyone for joining me for another episode of Handmade Hero. It's been a pleasure coding with you as always. I think we're basically finished with the sort of normal map cleanup stuff there. It looks like everything's working properly now. So next week, what we should be able to do, hopefully, is start to build those lighting sample buffers and then actually sample out of them using our normal maps that are being passed through properly now. It's going to be a little experimental next week because we really don't know exactly how, exactly what would be good ways to do all the stuff that we kind of want to do here. So yeah, it's a little wonky, but you know, we'll do the best that we can. Anything with lighting, even in a 3D environment, it's always a hack. Because simulating lighting correctly is too difficult. And so you're always coming up with sort of these approximations that are sort of what you're doing because you don't have time to do a full light transport solution on your scene. Obviously, you know, oftentimes those take minutes to do, even today. So you kind of have the situation where, yeah, we're not really at the point where we can do real lighting transport. So it's always an approximation, and that's okay. That's just where we're at. And so we will play with those approximations next week until we get something, or maybe even for 2 weeks, who knows how long it'll take us, but we'll keep playing with them until we get something that we feel like we can use as sort of the basis for our render setup, right? So I hope you'll join me for that. Same time, same place on Monday, I believe, although definitely always check the Twitter for the schedule, but I believe it should be 5 p.m. on Monday, same time, same place as it was today. So yeah, thanks for joining me. If you would like to follow along at home and want access to the source code, you can pre-order it on handmadehero.org and use the little pre-order button. That'll get you access to the source code if you want to follow along at home. There's also a Patreon page if you want to subscribe and support the video series. It's much appreciated. We also have a forums site where you can ask questions. You can also look at ports to Mac and Linux that the community's done there. You can also look at the annotated episode guide, which is pretty awesome. And we have a tweet bot as well, which tweets the schedule at you. So if you'd like to check that out, that's a good thing to subscribe to so that you know when essentially the show's going to be live. So thanks everyone for joining me. Hope to see you next week. Have a wonderful weekend, and we will pick up where we left off on Monday.